All right, boys and girls, welcome back to the drive-thru. Sponsored as always by the deli. Hungry? Skip lunch and donate your money to Josh Cares because it's a good foundation. Or go to lunch today and eat your lunch and donate your change to the Josh Cares fundraiser. All right, so we are picking up 14.1. This is the second video after yesterday's 25-minute epic long video that no one watched. So we are trying to determine if these two-dimensional vector, vector fields, we're trying to determine if these two-dimensional vector fields are conservative. So to do that, we're going to differentiate this with respect to what? No. With respect to y. Remember, what we're trying to figure out, how we ended our video yesterday, is we're trying to see if the mixed partials are equal. F sub xy equals f sub yx. Remember that we got this by taking the partial derivative with respect to x of some function. We don't know what that function is. Okay? Yes. Yes, it is assumed that. We are using the gradient as an operator, and you guys will get more used to what the heck that means as an operator as this lecture goes on. Okay? But yes, it is assumed from the definition that this came from a potential or a parent function, and so we're saying that x squared y was equal to some function of x and y, the partial with respect to x. And I'm just calling it p so you guys know that it's the potential or the parent function. Okay? Okay? All right. So, what does this equal? That equals x squared, right? Now let's take the derivative of this one with respect to what? With respect to x. And what does that give us? And are these two things equal? They are not. So, what did we learn? This is not a conservative vector field. As our third bell is calling it, that's a liberal vector field. I don't think you're ever allowed to use that in any other math class, but that's a good way to put not conservative. Okay? What's the derivative of 2x with respect to y? 0. Okay? And what's the derivative of y with respect, that's a j by the way. What's the derivative of y with respect to x? Are those equal? So what did we learn? It's conservative. So what does that mean? It means that some function exists and that this thing is the gradient of that function. So don't you feel like we should find it right now? Let's do it. Okay, now, here's where it gets really weird. What did we differentiate this with respect to do our test? Now, what are we going to integrate it with respect to find our potential or our parent function? X. We're doing the opposite of the gradient. So, what's the integral of 2x with respect to x? X squared plus f of y. No longer c. What's the derivative of a function that's simply of y with respect to x? It's 0. So we can't assume that this thing is simply a constant. Okay, so stay with us. We'll be all right. So what is the integral of y with respect to y? Y squared over 2 plus what? We'll call it g of x because f and g can be different functions. So what is our potential function? And this is not the same notation as the book, but what is p of xy? It's x squared What's our f of y? Plus y squared over 2. Right? Then plus c. Exactly. We're just using a convenient... If we know that when we integrate this with respect to x, it gives us this, but with the possibility of some other function that was only expressed in terms of y, let's conveniently use this as that function. And then we found out that the integral of y with respect to y was this, but it could also have some function that was a function strictly of x. So what do we call that? That. However, we could still have a constant involved. Does that make sense? Now, find the gradient of that. What's the gradient of p of x comma y? 2xi plus yj. Do you recognize that? That is, okay, got it? This is the original function that we had. So let's go back over what we did. What did we do first? We tested to see if it was conservative. Okay? Once we found out that it was conservative, that means that we deduced that this thing was the gradient of some potential function. Then we integrated it to find the potential function, but we had to remember what gets eliminated during the derivative process, and we had to account for that here, here, and here. Okay?
So would that say then, with that gradient?
Okay, real quick, let's find together the potential function here, or the parent function. Okay? So, what should we do before we seek out a potential function? We should test it. We don't want to try to find a parent function that doesn't exist. Okay? So, what's the derivative of this one with respect to y? And what's the derivative of this one with respect to x? And those are equal. So yes, it's conservative. So now we'll start. So we're going to integrate 2xy with respect to x now. Because remember, it got there by the gradient process. And so what do you get? X squared y plus, I guess I'll keep f of y, okay? And the integral of x squared minus y with respect to y is x squared y minus y squared over 2 plus g of x. So what is g of x? No, we don't know. G of x could be a constant, right? It couldn't be anything, I don't think. Look, this is that. So we're going to call our g of x c, okay? So our parent function is equal to what? Nope. Just x squared y. You got it. It took care of itself in both of them. And just watch. When we're done, we're going to take the gradient, and as long as it leads us back to where we started, we'll be confident that we did it right. Okay, we had a little break. Okay, so minus y squared over 2. And then, class? Plus c. Now what's the gradient of that? Plus what? And does that make you confident that you found it right? Okay, good. All right, so the next thing we're going to do, unfortunately, we're going to learn curl before we learn divergence, because curl gives us our test for a three-dimensional vector field, okay? But I would prefer to learn it in the other order because we learn dot products before cross products. But you're going to have to remember dot products and cross products, okay? So, first of all, let's just write this out. Test for conservative vector field. In 3 dimensions, okay? So, if curl of f of x comma y comma z is equal to 0, then f of x comma y comma z equals mi plus nj plus pk is conservative. Now, you don't understand what curl means yet, so don't freak out. But that's why we're going to do it in this order, because I think that logically follows how we've done this lesson so far. So now we do have a test for 3 dimensions. It's just going to be a little bit more involved than our 2-dimensional test. But that's nice. We won't have to try to find a parent function before we can test it, okay? All right, so what is curl? All right, well, what it actually is your inside a vector field at a certain location. It is an object's willingness to rotate and the axis at which it will rotate around. So imagine you've got like a, here's your finger, okay? Here's your fingernail. And then you stick a pin in your finger, okay, which would hurt. And then out of this little pin, you create like a little pinwheel. And so out here is coming like that, and then there's one in the background. Can you imagine that? Okay? And now you're in the wind, okay? So there could be a time when you were in a vector field that had vectors like that, so all of the wind was congruent at all places. So if that was going, say, this way, what would happen to our pinwheel? Nothing. Very good. Okay? It would not curl. Does that make sense? Because an equal amount of wind would be hitting it there and there, so it wouldn't rotate. But if our vector field looked like this, and that's what it looked like, now what would happen? It would curl. Now eventually we're going to learn the right-hand rule, which is kind of like cross products. So if you take your fingers and you curl them, your thumb will point to the positive direction of curl. Okay? Got it? Okay, so that's the best way I can introduce you to curl, but we'll get way more involved with it. But I want you to kind of have an idea of what you're figuring out before we learn the math behind it. Now, the next thing you got to understand is that when you see this thing, del, and it's by itself, it's just an operator. Without accompaniment, it does absolutely nothing. But by itself, it looks like this. And I hope that looks familiar, because del f of x comma y comma z, what was that equal to? Oh shoot, yeah, that should be a z, thank you. What was that? This is the old school gradient notation. What was it? It was dx, it was the df dxi, not plus, yeah, plus df dyj plus df dz k. Okay, so I just want you to remember that you've used del as an operator before. Okay? All right, so here's how you find curl. Curl of f of x comma y comma z is equal to it's equal to del cross f. Okay? So here's where del goes. And then at the bottom, you'll have, remember that f of x comma y comma z, according to like our definition of a vector field, is m I plus n j plus p k. Do you remember that from yesterday's video? Okay, so down here we just put an m, an n, and a p. So what we're saying to you here is we would never expect you to memorize the formula for the curl, but luckily you've already memorized how to do a 3 by 3 determinant. Okay, so curl of f is equal to, anyone want to do this for me? Go ahead, Josh. dp dy minus dn dz I, and then minus, yep, dp dx minus dm dz j, don't forget this minus sign, and then plus dn dx, weird ends today, minus dm dy k. Okay? That's how you find curl. So what does curl give you? It gives you a vector at a point. Okay? And curl changes at different parts of the field. Okay, so if we could apply curl to our original explanation, what curl is measuring is the rate of change of our forces at a given point. And so since this thing would be willing and easily rotatable, okay, since it would be changing there, then we know that we have a significant change of force at that point. So a high curl vector indicates willingness to, in this case, spin around, okay? Whereas if our vectors were constant, like in our original example, our curl would be 0 there because there's no change of force. Did you say that's accurate? Okay. All right. So what we found here is how to find curl. What did we use to find curl? We used a cross product and an operator, okay? Raquel? Okay, so now we're moving on to divergence, okay? Now, we'll go about this backwards. We'll start with the math this time, okay? So divergence is del dot f, okay? So divergence of f of x comma y comma z is del dot f, okay? Now, it's hard to understand this, but what they're basically telling you to do is if you had, let's see, f of x comma y comma z equals, let me just find, and let's say x cubed y squared z I plus x squared z j plus x squared y k. Okay, now look, in this example, that is m, this is n, and that function is p, okay? Okay? So, what you're going to do, what this is really telling you to do, is to do d dx I d dy j d dz k dot, so the operator is much less useful here, okay? Dot x cubed y squared z I plus x squared z j plus x squared y k. So all you're doing is basically taking, well, that's not true, because the gradient was of an original parent function. But you're taking the partial with respect to all of these. So the partial of this one with respect to x, the partial of this one with respect to y, the partial of this one with respect to z, but then you're adding those components. Okay? So let's find the answer, and then I'm going to answer your question. What divergence is telling us. Okay, so remember this is a dot product, so we get a constant. So what's the derivative of this with respect to x? 3x squared y squared z plus, what's the derivative of this with respect to y? Plus 0 plus 0. Okay, now, we wanted to find it at the point 2, comma 1, comma negative 1. So let's say we just wanted to see what it was at a certain point. Okay, so you plug that in, and what do you get? Negative 12. Okay? Now, I can't explain to you what the magnitude of that is telling us, but I can explain what a positive divergence, a negative divergence, and a zero divergence would give you. So, let's say we had something like this. So, as we get away from a certain point, our force is increasing, okay? And we have some object here in that force field at a certain point. If that, it has nothing to do with the movement. If that object is getting expanded, do you see how these vectors are getting bigger? So then if we had an object that was made up of more than just a single point, if it's getting expanded, then we have a positive divergence. Okay? This is going to be important in fluid dynamics when things are moving through things and changing while they're moving. You can imagine that if something was expanding, it would be getting less dense, and it might be more willing to move through. And if something had a negative divergence, so that would look like this. It would really, I don't know. Do you have a good one at mind? Right, it's not only the vectors, but it's what's happening to them. So, like if I did here, you have a negative divergence. It's getting contracted. Okay? Yeah, all 14.1. Okay? And now here, this particle would just be getting moved. It's in a force field, so force is acting on it. So it is feeling force, but it's not changing magnitude, only location. And this would be zero divergence, okay? You too, Ratchet. Okay, so summarizing some things. Divergence gives us a constant or a scalar as the answer. What Mr. G hypothesizes is that that represents the change in the magnitude of the vectors in a field. So here you can see that at this point the vectors are getting smaller. That's why I've indicated that the divergence would be negative. At this point the vectors are expanding, and that's why the divergence would be positive. By what point they're expanding probably has something to do with how big this constant is. And then here, the vectors are not changing, so the divergence, the change in the size of our vector, is equal to 0. That's not to say that we're multiplying it by a factor of 0, and so that's where the calculus comes in. This negative is referring to change, not that we're changing the direction of the vectors. Now, going back to curl gives us a vector. Okay? So, what that is representing is the change of direction within the field. And so, since there's both change in magnitude and direction, the magnitude of that vector might indicate the willingness of something to rotate, and then the orientation of that vector may indicate which axis or about what it will rotate. So, thanks for sticking with the video, and if you boys are in Chicago watching it, I'm proud of you. Boom!